Up and running. All right, so this is a lecture on the geometric principles of conversion associated with linear, quadratic, cubic, quadratic, and beyond. Really trying to get at something that students have a little trouble with, which is how to write this equation as quickly as they can write the equation with a line, which should be 10 seconds or less. Understanding conceptually what's going on here seems to be a stumbling block. So I want to try to talk about that, do some geometric drawings, and we'll start with the linear. We'll chat about it a little bit, but the quadratic and the cubic are closely behind, and we'll see if we can make some gains here. All right, so that's our goal, be able to geometrically see what's happening with this quadratic. All right, which can be written in the form of ax minus h squared plus k. And we're going to talk about conversion principles. All right, so let me move this down a little bit. I don't think mx plus b is helpful. I wish we wasn't in any textbooks. I think we're better off with an ax plus b model, which can then be written in graphing form. Ax minus h to the first power plus k. Notice I'm writing this even though I don't have to, because I believe that one represents a one-dimensional picture, whereas the two, a two-dimensional picture, and the three, a three-dimensional picture, and then my drawing stop. Okay, but each of these has governance of conversion. As to what governs the conversion here is a little bit different. It's one operation different in each case. Oh, well, the cubic is a little more complicated. I should take this back. It still follows the conversion principles, but it is a little more complicated. Okay, so let's see. And minus b over a, minus b over 2a, minus b over 3a, minus b over 4a, so on and so forth, are simply ways to write fewer terms in each of those models, which means you have fewer graphs to consider the interplay of those graphs leading to one graph. All right, that may not mean anything to you yet. But let's look at the, well, I was going to look at the linear, but we're going to jump right. Yeah, we'll look at the linear here. All right, so linear conversion. And I'm going to look at something written in this form. Okay, which is one step away from point slope form. I mean, there's no great difference. I like this form best. It's not in the textbooks written that way, but I wish it was. I think it gives you a left to right orientation for the brain. We can see a 3 gets us an 11. Okay. And this is one-dimensional change from the number 3. That's what the parentheses x minus 3 tells us. We're looking at one-dimensional change from the number 3, except we don't write the 1. And we're going to double that change. We're going to double that change from 3. And then we're going to add 11. And I think we can see that we have one place on the graph, 311. And how would we find other places? Well, we have to get other numbers, like 4. And if I move over to 4, to me, that's one-dimensional change. And it's one unit of change. And if I double that change and add 11, then 4 gets me 13. And if I wanted to talk about how far is it from 3 to 5, now there's a subtle language difference there, right? From 3 to 5, the brain processes 2 units a little easier than saying y2 minus y1, or I'm sorry, in this case, x2 minus x1. And how far do you get from this number to that number? Brain processes that easier than saying, what's the difference between 5 and 3? How do you get from 3 to 5? Well, you go up 2. What's the difference between 5 to 3? Well, you had to actually listen to that just a little bit more. All right, and so if we look at that, I see this as a line. And that's 2 units of linear change. And if we double it, we get 4 plus 11 is 15. And we can quickly see a pattern emerging, right? We can quickly see that the x's are changing by 1. And the y's are changing by 2. Right? I mean, if we go to the number 6, how do you get from 3 to 6? 3 units of linear one-dimensional change. And 6 gets us 17. Okay. So it's really easy to graph a line. You can get 2 points quickly and easily that way. But then the issue is, what if we didn't want 13? What if we wanted 14? Well, let's go to this one. Let's go from 3 to 5. And instead of 15, what if we wanted 19? A new number. Well, then we got to start and think about it. And we go, well, 3 to 5 is 2 units of linear change. Okay, and if we double that, we've got 4 units of linear change plus 11. And unfortunately, that does not take us to 19. We got a marker. We're not going to change the 3 and the 11, but we can change the multiplier. We can make this change of 2 turn into the change we want. That sounds like a political ad from years ago. Okay, so how do we change that 2 so that it becomes the change we want, which is 7, because we said we wanted to go to 19. We got to turn this 2 into a 7 and then add 11. Now, I'm not going to use addition or subtraction to change this number because I already have, and it's in concrete. So what's my other choice? Get rid of the 2 and add 8. Get rid of the 2 and add 8. That's a multiplication by 4. Right? Because that's a change of 8 to 2. And I think now if we put the number 5 in, 5 minus 3 is 2. 2 times 4 is 8. 8 plus 11 is 19. So it looks like we changed this by canceling the linear change that we didn't want to make it a linear change that we did want to go through the data that we wanted it to match. All right, so now we go up 1 level of difficulty. We have established that x minus 3, the parentheses x minus 3 measures change from 3 on a number line, because I really was drawing a number line. But what happens when I square it? Let's find out. Let's go to 4. Well, that's linear change. This is quadratic change. I get 1 unit of quadratic change. And if I double that and add 11, 2 plus 11 is 13. That's the same as what we had before, a little while ago, but it's about to change now. So let's go and look at what happens when I go to 5. Well, that's a new picture. The linear change is 2, right? The linear change, this is the linear change, and that's what we just did, put a 5 in there. But we're after the quadratic change. And the quadratic change is actually 4 units. And if we double that, we multiply it times 2, looks like we got 8 plus 11, it's 19. Now I did something stupid here. 8 plus 11, 19, 3 to 5. Oh, I changed, that's right. In order to make that happen, I doubled it. Okay, we're good. All right, and what happens if we go to 6? Well, new picture. 6 from 3 to 6 is 3 linear units of change, but the quadratic is now 9. And if I double the 9, I get 18, and 18 plus 11 is 29. I'm starting to see some, this changed by 2, that changed by 6, that changed by 10. Interesting. Oh, this was 7, 6. Yeah, that's right, 6, 10 units of change. And what happens, we'll do one more. Let's go to 7. Let's go from 3 to 7. Well, to me, that's 4 units of linear change, but quadratic change at 16. And if I double that, I get 32 plus 11, 43. This is not linear change. These are all changing by 1. You know, each side of the square is going up by 1. I'm getting significant change there. Yeah. And in between, right? More and more distance in between. And that's what gives us this kind of lifting process, right? This is a minimum, right? Because what's the smallest square area we can have? The smallest one we can have, because those are just getting bigger, is 0. I can't really draw it. 0 times 0 is 0. So I can't really draw it. And I think I'm yelling too loud because there's a class next to me and my wife's teaching it. All right, so quadratic change then helps us to be able to do what I put on the board to begin with. Let's say we have 7, 5. Well, you can certainly write x minus 7 squared plus 5, right? And what if we wanted to go to, oh, let's say 11 100. Okay, not new problem. Well, 7 to 11, measuring from 7 to 11, that's that's linear change. Before the quadratic change is 16. And I don't think 16 plus 5 is going to take me to 100. So what do we need to do? Well, first thing we need to do is measure quadratic change from 7 and an initial amount of 5 when we put a 7 in. And then when I drop the 11 in, I should draw it again. 7 goes to 11, but quadratic change is 16. And that number didn't take us to 100, so we get rid of it. What does take us to 100? 95. That doesn't appear to me to be much different than the linear process. I hope I got through that all. Okay, so let's just do a couple of these real quick. See if you can do them with that understanding, hopefully. Let's look at, and there's symmetry, of course, right? I could have looked in this direction. I haven't been. All right, so let's look at 2, 5. Well, I just used a 5, so let's use a 7, 2, 7, and let's go to, let's go to 12, 30. Okay. Well, the pattern emanates from here. So x minus 2 squared plus 7, okay, gets us started. These are our y values, yes? Can you see all of that? Yep. And what happens when I go from 2 to 12? Well, I'm going to have to make a smaller drawing. 2 to 12, what happens? Well, I have 10 units of linear change, but two-dimensional change is not linear. Linear is one dimension. So the real change here is 100. And I don't think 100 plus 7 takes me to 30. So we get rid of that. Instead, 7 to 30, 23. And that's how you can write those quickly and easily. So let's look at the cubic. And we'll be studying cubics after midterm. And I probably won't talk too much longer here. But what is cubic change? It's three-dimensional change. So let's say I wanted 311. Okay, and ax minus h cubed plus m x minus h plus k. That's the graphing form for cubics. I don't think it's in the textbooks. Should be. This is the richest pre-calculus calculation available to us. It affords all kinds of opportunities to talk about the concepts that you're gonna be looking at if you take a calculus course. But I am not going to look at the tail end of this. We're not ready to look at that, but we can look at three-dimensional change. And let's go from 3 to 5. What's the three-dimensional change? Well, I got to do this lower. 3 to 5. That's linear change, right? 3 to 5. Cubic change is this. Right? So if that's 2, the cubic change is 8. Right, so if I wanted 311 and I want to go to, let's go to something not too, let's go to 8. Let's go from 3 to 8 and let's go to 20. but so let's go to 26. Yeah, that's not too bad. All right, so if this was just this part, if that's all we were gonna do is that, not with the linear component, then I think we're at a x minus 3 squared, cubed, sorry, plus 11. Okay, and what we would get is a cubic that looks like this. 3 gets us 11. And notice it's pretty flat here, right? And the reason it's flat there is from 3 to 3, there's no change in the cube, right? As I go to 4, I start to get a, a certain size cube. If I go to 5, it's a bigger one, right? And so cubics change by increasing the dimensions, say, just by a couple of, a thousandth of an inch, say these are inches. Thousandth of an inch is going to give us a new layer of change. Well, if you don't have a box, you can't get any change. And that's why it's flat there. And just trying to plant a calculus seed. Okay. So how do I make this work? Well, once again, we need the linear change from 3 to 8 is 5. But what's the cubic change? I hope you're saying 125, right? 5 units times 5 units times 5 units, perfect cube. All right, so we don't want 5, and we don't want 125. We don't want that change because that change plus 11 doesn't take us to 26. What takes us to 26? 11 to 26, 15. Okay, now I could divide by 5, make that a simpler fraction. But these are the conversion principles. If you've got a shape, you create, in this case, volume in the quadratic, area in the linear length. And if you put a number in to where you're measuring from, and the change doesn't take you to your second coordinate, then you have to get rid of it. And what gets rid of it? Addition and subtraction gets rid of the first part of conversion. But the second part, the more complicated part, division. Very easy to turn the number 5 into the number 11 with multiplication. What do I have to multiply 5 by to get 11? 11/5. Get rid of what you don't want, bring in what you do. And that's what's kind of weaving its way through these processes. All right. I was going to show you some more things about minus b over a, minus b over 3a, 2a. Enough. All right. This is, if you can make this connection, you've come a long way. So I hope that you think about it because it really opens the door to what's really going on from a geometric perspective. Everything in math, I think, comes from those relationships. All right. I can't talk any louder because I'm going to get in trouble. Bye-bye.